In this video, you're going to understand what measures of dispersion actually means. We're breaking down the 4 statistical forces that define the variance in any given data set. Those are range, variance, standard deviation, and standard error of mean. The very metrics that can make or break your interpretations. And we're going to give examples for all of those. My name is João Evangelista, and this is the Meta-Analyses Academy, where we teach thousands of students worldwide the science of making systematic reviews and meta-analysis. We begin by discussing why measures of dispersion matters, how understanding the measurement of variability can help you complement your understanding based on the measures of central tendency, which we covered in another video. If you don't understand mean or average, mode, and median, you potentially would be better off if you went to this other video, pause this one, go to the other video, and then understand all these subjects and then come here. But I'm assuming you already know these topics, and even if you don't know, I'm gonna give context all over this video. Like, your time is short and you just want to learn this topic as soon as possible, I'm gonna give that here too. But just know that it would be better if you were more in-depth into those other concepts before you understood this one, just because those are more fundamental. Next, we explore the 4 measures of dispersion. Those are the range, the variance, the standard deviation, and the standard error of the mean. And I'm gonna give examples to each of those concepts. All right, let's go. First, we need to understand what even is dispersion and why our statistical references should probably calculate those. Dispersion pretty much means which parts of your data set deviate from the average that you chose, your measure of central tendency, and by how much they deviate from that measure of central tendency. You can imagine 2 groups with the systolic blood pressure with an average of 120. Let's say that one group has patients with 118, 119, 120, 121, and 122. Okay? The average for this group would be 120. Let's say that you have another group with, say, 20 patients that have measures of systolic blood pressure ranging from 90 millimeters of mercury all the way to 170. But let's say that you calculate the average and it's also 120. You agree, I'm sure, that even though those groups have the same average, they don't behave the same. They have massively different statistical inferences about them. They're not the same group at all, and probably the second group has a much wider range, probably a much higher clinical instability. Regardless of the differences between those two, you should at least understand that these 2 entities, these 2 populations are going to behave differently mathematically speaking. What we can correctly say about one population is not necessarily correct about the other population, even though their averages are the same, okay? And this is where deviation comes in. By how much does the numbers deviate from the average number calculated? Hopefully you do understand that the first group, the one that had 118, 119, 120, 121, and 122, that number has a much lower level of deviation than the other one that has 20 patients, and then some ranging from 90 millimeters of mercury and the other like all the way up in 170. You know what I mean? Like, this is a much larger deviation from the average. All right, so first, let's talk about range. Range is the simplest measurement of dispersion. It's pretty much the maximum value minus the lowest value. From that first population, we had 122 millimeters of mercury minus 118 millimeters of mercury, giving us 4 millimeters of mercury as the total range. That's how much it deviates, 4 millimeters of mercury. But the average is still 120. But the range for the second group is different. It's 170, which was the maximum value, minus 90, which was the lowest value. One thing that needs to be said is that this is very sensitive to outliers. The first group that we looked on had 118, 119, 120, 121, and 122. All right, let's say that we give like just one patient more, but this patient has 200, all right, of systolic blood pressure. A range that was 4 is now 82. Even though most of the patients are in that 4 millimeters of mercury range from 118 to 122, and those are more representative of the population that we're now studying, there's that guy over there with 200 kind of messing up our calculations. And then when we look at the range, like 82, we're like, well, like, why is the dispersion so big, And it really is not. It's just the range itself, without any other metrics, is very sensible to an outlier like that. It doesn't mean that our data is incorrect. It just kind of looks weird, and it doesn't allow for a person that's just looking at the range to infer that that is a study with little heterogeneity. When you look at that pool of data and you only have the range, you say, well, they have 6 patients and the range is 82, so the data is probably all over the place, when it really isn't. It's just an outlier messing things up. Next, we need to understand 2 concepts that are kind of mathematically difficult, but bear with me, you're gonna understand it. Variance and standard deviation. To understand variability with more precision, we need standard deviation. Those are 2 of the most important, most reliable tools in statistics. Make sure you understand this part. Let's start with variance. Variance measures how far any data point is from the average on average. I'll repeat it because this enunciation is difficult to understand. Variance measures how far each data point is from the mean on average. So in order to calculate the variance, first we need to calculate the average, or mean. You calculate the average by gathering every single value and dividing it by the number of values you gathered. In order to get the variance, what you need to do is you get the differences between every single value and you square them. So just to recapitulate, you find the mean and then you reduce every value from the mean and then you square those. You might say, like, why do you square them? You square them because you don't want the negative values to cancel out the positive values. Every number below average is going to be like a negative value, and then every number, like above average is going to be like a positive value. But those are going to be squared because they need to be positive, like all positive numbers. Let's say that our average is like a bullseye, and then every other data point are like darts in the bullseye. If we measure the distance, what we're trying to do is gather up how far each dart is to the actual average. So even though we're going to have negative values, it's not negative distance. It's like a road cannot have -2 kilometers. So it really helps if you see dispersion as a distance from the central tendency. You got what I mean, right? So for populations, to get the variance, you sum all the squares from the differences between the value of each data set and the average between every value on that data set, and then you divide by the number of values, by the number of persons analyzed in that population, by the number of data collected, you know what I mean? So in order to get the variance, what you need to do is to sum all the squares of those differences between each value and the average. And then you divide by n, and n is the number of values that you actually collected. Now, when you're working with a very large population, you need to get just like a sample of that. And when you're studying the sample, instead of dividing by just the number of persons you got from the sample, you divide it by the number of persons minus 1. When we get a sample size and the sample size is very small in comparison to the population, we tend to underestimate the variance if we just divide by n. However, if we divide by n minus 1, this is better. Explaining exactly how that math works is outside of the scope of this video. Just know that if you want to Google that, this is called Bessel's correction. I hope I'm pronouncing that correctly. Bessel's correction. Now, regardless if you were paying attention to that part of the math, that particular part of the math, the squares, the sum of everything, and then you divide by n or n minus 1, whatever. But one thing that's important to keep in mind here is that variance is a squared unity, which means that let's say that you're calculating systolic blood pressure. The unit is going to be like millimeters of mercury. But, like if you calculate the variance, you have millimeters of mercury squared. And that's not intuitive. Like our minds kind of can't comprehend that. What even is pressure, which is millimeters of mercury, squared? Also, those numbers that were squared can be very huge, or if they were between 0 and 1, they're going to become even smaller. So what do we do to correct for both of those problems, like the large or very small numbers and, the measurement of the unit squared. What we do is we take the square root of the variance, and that is standard deviation. It's pretty much a better way to observe virtually the same thing. Standard deviation allows our minds to better comprehend variance. Okay? That's pretty much it. Let's say that the variance was like 100 millimeters of mercury squared. If you take the square root, you're going to have 10 millimeters of mercury. And that's a much more like organic number to work with. It's only one dimension, it's not squared. Now let's talk about the last part, the standard error of the mean. Let's say that you have a huge sample size. You're not going to be able to study all of that, okay? You're not going to be able to study every single person. So what you do is you take a sample. So you gather the data from just that group, and then you can calculate the mean and all that good stuff. So what standard error of the mean does is it allows us to know how precise is the measurements that we made based just on those people that we collected, just that sample. How precise are those averages, those numbers that we collected, that we inferred, in relationship to like the whole population that we started with? That's really amazing to me. The fact that we can infer for the general population things that were taken just from, a group of less than 10% of that population or whatever, like a small sample. The fact that we can do that is the only way we can have viable research. Let's say that you're trying to study malaria. If you had to gather every single patient with malaria all over the world to do a study, that would be so impractical. Research would be just not possible. But how sure can we be that we need to get just some people with malaria and then infer for the general population that has malaria things that we took from that small group? How sure we can be that the things that we took from them are actually applicable is calculated by standard error of the mean. And provided that you already have the standard deviation, calculating this is far simpler than calculating the standard deviation to begin with. All you do is you divide the standard deviation by the square root of the number of values you collected. So just as a recap, you get the standard deviation and then you divide it by the square root of the number of values you collected to begin with. So the standard error of the mean is not just any number. It's like how strongly is a data that I got from a sample applicable to the entire population. And that's really powerful. That's the backbone of statistical research. If I'm studying a disease and I have like 100 patients, of course I want the best for my 100 patients. But what I want to do is conclude how can I treat everyone all over the world that has that disease, and standard error of the mean makes that possible. So yeah, go do that. And all right, that was really it. Let's review now everything we made in this video, just to make sure it really sticks with you. All right, so the range gives you everything, like everywhere your data could possibly be. It's the maximum value minus the minimum value. So variance and standard deviation go one step further. They're mathematical calculations that show how much each data point drifts away from the average. This allows you to understand how close is every point in your data. If you have a small standard deviation, that means every data point is close to each other. If you have a large standard deviation, then everything is scattered. And then standard error of the mean goes even one step further. When you calculate the standard error of the mean, you're able to infer from just a sample size things about any broad population that the sample size is originally from. So in meta-analysis, mastering those concepts is crucial. It's not optional. You need them to understand forest plots, heterogeneity, comparing the confidence intervals with the no value, and comparing studies amongst themselves. All super important stuff for anyone that wants to go far in statistics. Alright, that's it from us. I hope you now understand how measures of dispersion really work. If you have any questions, please leave it in the comments below and we're going to try to answer them as soon as possible. Alright? Great! See you next time, guys.